we will be seeing how to find the number of islands in a given 2D matrix and also compute the time complexity and space complexity of the solution that we will be building in JavaScript. We will be using depth first search to reach a solution. And before jumping into the solution aspect of it, let us first try to understand what is a problem statement. The problem statement says that given a 2D matrix, something like this, wherein you will be having an array of arrays which makes it a 2D matrix. The ones in the matrix are going to be representing ones and zeros in the matrix are going to be representing water. So this is land and this is water. What we have to do is, from this matrix we have to find number of islands that can be formed from this specific input that you receive. And it says that we can assume that outside the scope of the matrix, whatever lies is going to be water. What that means is basically beyond this point below, it's going to be all water. Here it's also going to be water, and on the other edges also it's just going to be water here, whatever you have. So this is water, this side is water, this side is also water, this is also water, and so on outside the scope of the matrix. And this ones represent the land mass that exists, and from this input we have to figure out the number of islands that can be formed. And the islands can be formed by adjacent land masses which are either horizontal or vertical. So if I consider these two vertically, this can also form one island. If I say this and this can also form one island. And if I consider all these three at once, horizontally and vertically, then that can also form one chunk of island. And we have to find this unique islands from this input that we receive. So that's basically the problem statement. And to reach a solution, we said we will be using depth first search. Now why depth first search? What we can do is we can try to find a piece of land and see the adjacent piece of land that exists next to the node that we start with, and see what is the chunk of land that it forms. Whatever chunk of land it forms. What I mean by chunk of land is this. Now I can see here this forms a landmass and here there is water. But this chunk which is formed here can be considered as one island because this is all connected, and that's why in the output I'm saying here this is going to be 1 because we have to return the number of islands that can be formed. Now here, this whole chunk, how do we find this chunk? To find this chunk, we use depth first search. We will start from this node and we will traverse all the way and see what is the connected landmass that you can find. That connected landmass is going to be an island, which translates to DFS of traversal to find the connected components in a graph. That's why we are going to be using depth first search. Let's first try to explore how we can convert this into a problem statement of depth first search. Now, what we can consider this is each node in the matrix can be considered as a node in a graph, and we can say if you have 1 and 1, then you can connect this. If you have 1 and 1, you can connect this basically horizontally or vertically. And what I mean by connecting is this is going to be a undirected graph. So this and this has a connection, this and this also has a connection, this and this has a connection, this and this and this also has a connection. This and this is 1, so it can be connected. This and this is 1, similarly this can be connected, and this represents a undirected graph with its nodes. Now what we have to do is start from a node and do depth first search. And then what will happen in depth first search is basically we're going to mark these nodes as visited as we go through the matrix based on this undirected graph. And how that is going to happen is, let us say you start with a stack. So I will be using a stack because for depth first search we use a stack. What depth first search is going to do is start a node, put it in a stack, and then keep going deep inside that node to find the other connected nodes that are not visited, and keep repeating this pattern until everything is visited which can be possibly visited. So now what we will do is, let's take this representation and we will say the order which will be follow is something like this. I will try to see if I can from a specific node go to the top of the node, then I will see if I can go down, then I will see if I can go left, and then I will see if I can go right. This is the order I'm going to be following for traversal in my depth first search order. Reason being that in this the graph is connected if you have one here, so if it is len, it is connected adjacent, and that's why I said we can follow this top down left right order when we do this DFS. So what we will do is basically start with this node. Let's say we will mark this as A. From A I will put this A in the stack. I will check whether I can go to top or down or left or right after I have marked this node as visited. So as soon as I put it in the stack, I mark the node as visited. I will cross it out here and I will say this is my visiting order. So I will start with A. Then I will say, hey, can I go on the top? On the top there is water, so there is no connection, so I cannot go on the top. Then I will say, hey, can I go down? I see there is a 1 here, this is unvisited, so yes, I can go down. If I can go down, I will be saying that let's just for the sake of simplicity mark this as B, and I will put my B in my stack. I will mark my B now as visited, and I will put B in this traversal order of mine, and then I will say from B again, can I go top? I will see from here the top is already visited, so I cannot go top anymore. I will say, hey, can I go down now? From B I can go down, so let's go down. For the sake of simplicity, I'm just marking them as we go with alphabets, so it's easier to grasp. So I will say C, which is this one. I will mark C as visited now, and I will put my C here. From C again I will check, hey, can I go top? Top already B is there, which is already visited, so I cannot go on the top. Can I go down? No, there is nothing below. This is 0, so there is no connection here, so you cannot go down. Then I will see, can I go left? No, you cannot go left. This is also water, which is 0. And can I go right? Yes, I can go right. So from here I will go right. I will mark this as visited, put this D in my tracker. Now from here again I will say mark this as visited and check again, can I go top? From here I am able to go top, so I will just proceed with going here. I will mark this as visited, let's call it E. So this is E, and then from here I will again check, can I go on the top? Yes, I can still go on the top, so I will mark this as F. I will put the F in my stack. I will say the path is F. I will mark this as visited. From here I will again check, hey, can I go top? There is nothing on the top, so I will check down. Down I have already visited. Left I have already visited. Right I have not visited, so I will go on the right here, and I will say put this in my stack as well, and I will mark this as visited. Now from here what I will do is again follow the same pattern. Can I go on the top? No. Can I go down? No. Can I go left? Already visited. Cannot go left. Can I go right? Yes, I can go right. So I will mark this as H. I will put it in my stack. I will also put it here. And then I will mark this as visited. I will say, hey, from this, can I go top? No. Can I go down? Yes, I can go down. So I will mark this as I and mark it as visited, put it in my stack. Now at this point, what I will do is, here I will check, hey, can I go on the top again? No. Can I go down? Nope, not possible. Can I go left? Not possible. Can I go right? Not possible. So I will just pop this from my stack. Next, after I pop, I have H. From H, I will say, hey, can I go top, down, left, right? Not possible. I will pop this again. I will go to my G. I will say, hey, can I go top, down, left, right? They are already visited. So I will just keep popping my stack and stack becomes empty. This is my sequence that I have. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's one connected graph which I could find, which is my island. This is basically what we are going to do. After we find one island and mark all the nodes as visited, we are just going to try to find next island in the matrix and keep repeating the same process. This is the logic aspect which we are going to be following. So that's why we are calling this as a DFS approach, wherein we will find a node, keep going deeper into the node as long as it's possible to go based on the connections that exist, and then mark all the nodes as visited. And once you have found this connected graph, you are just going to mark this as +1 in your island count. And that's pretty much it. Now, in terms of the approach, we could have also taken a depth first approach and a breadth first search approach. With breadth first search approach, we could have used a queue and done something similar. But in this example, we are just proceeding ahead with the depth first search approach. And now that we have built a solution format, let us translate this into code. Let's start with the counter of islands that I'm going to use. So I will say let island count is equal to 0, and in the end I'm going to be returning this island count that I'm going to keep track of. And we said we are going to have the DFS traversal approach. So I will just say here DFS. I will take rows and columns representations, and I will either return true or false from this to ensure I can keep increasing the count if I have found the island. And when I find an island, which is going to be 1, I will try to see if it has connected parts of island to it. That is going to be my connected graph. And if I find it, I'm going to just mark everything is visited so that I don't have to revisit it again and my count doesn't get corrupted when I try to calculate the final count of my islands. And what I'm going to do is just use a tracker. I will go until the length of my grid, and I will also say J will go from the 0th position until the length of your ith entry that you have. So I will say this and J++, and here I'm going to say island count plus equals whatever this DFS is going to be giving me for your current I and J values. And just this loop part, we keep a counter and we do depth first search traversal here to find the connected nodes. And if it is part of a connected graph, whatever nodes I visit, I'm just going to mark them as visited. So let's say you got this node in the grid. What I'm going to do is, in the grid, I'm just going to be marking the node as visited. That means I have visited the node already. And another step is, first I have to check whether I can visit the node or not. If it's a 0, that is, it is water, I cannot visit it because it's not going to be part of your connected landmass. So I can just directly say that if grid of x and y is 0, just return 0 itself. And this will also cover the visited use case, wherein I'm going to say that if I have already visited it, I will just mark it as 0. And then if you have visited it, or if it's already water, then you are just going to return 0. You're not going to be taking it into consideration, because if you have visited it, that means you don't want to repeat it in your counting sequence when you try to find the connected nodes count of your inputted metrics that you have. And after I mark it as visited, what I had done was I come to a node, I mark it as visited, I crosses out, and then I say, can I go top, can I go down, can I go left, can I go right? So for that, what I'm going to do is something like this. Just say DFS, and for top, the representation is going to be x, which represents the number of rows, -1, y. Then for down, it's going to be x plus 1, y. Similarly, for left, it's going to be x, y minus 1. And for right, it's going to be x, y plus 1 in terms of representations. So I will say go on the top if you can go down if you can go left if possible, and go right if possible. Visit a node, check all the possibilities. If it is possible, do depth first search, go deep down. And in terms of the call stack, which we mentioned here, that we were keeping track of in this section, this is going to be based on these recursive calls. So whenever you do the recursive call, it's going to be like put in the stack, and then when you exit from the recursive call, when you return something, that is just going to get popped from the stack. And we are going to pop it from the stack if it doesn't have anything else you can visit, which is basically means either it's a 0 or you have already revisited it. Because if you revisit, then when you visited it the first time, you're setting it as 0. So when you revisit, it's going to be 0 and it's just going to exit. So this is going to be taking care of the traversal in all 4 directions. And then we also just need to make sure we are not going across boundaries. So if x is less than 0, or if x is greater than grid dot length, or if x y is less than 0, or y is greater than grid of x dot length, then also you are supposed to return 0, because if you're going out of bounds, then you don't want it to break. So greater than equal to the length, greater than equal to this length, so that you don't go outside the bounds. And then you return 0 if you have already visited, or if it's water, you return 0. And once you have visited it, once you have marked all the nodes in the depth as visited, you just return 1 to make sure that this acts as your counter. So you have completed the DFS part of it. You're just going to check your count and then return your count. And I is going to go from 0 until the length of your matrix that you have. So from 0 to I less than grid dot length, and j is also going to be going from j of 0 to the grid dot length, not less than equal to, it's just less than, because the index starts from 0. And that's pretty much it in terms of implementation that we have. And this is going to be running in terms of time complexity. It's going to say big O of m into n, where m is the number of rows, n is the number of columns, because every time you get your input, you're going to run this nested loops. So this is going to be m number of rows, this is going to be n number of columns, and from 0 until the length. And in terms of space complexity, it's also going to be big O of m into n. Reason being, this is going to go into recursion. So every time you make a visit to a node, you're going to see if you can possibly go top, down, left, right. Every time you make a call, it's going to go inside depth and recursively going to make the call until you reach the leaf node. and when you cannot go in any directions, it's just going to get popped by this return of 0, because we are saying if it's 0, just return 0, and then it's just going to get popped. And that's pretty much it in terms of the implementation. I hope you liked the video. Please like and subscribe.